Every morning, Arjun rows across this river to reach school. Seems simple, right? But there's a problem that has confused students and boat captains for centuries. The river is trying to trick him, and physics is the only way out. Arjun points his boat straight across. He's strong, he rows hard, but look what happens. The river current, flowing at 4 meters per second, keeps pushing him sideways. He crosses the full width, but lands 200 meters downstream. He missed his target completely. Why? Because velocity is a vector, and two vectors are happening at the same time. Here is the secret. Arjun's boat moves at 3 meters per second through the water. The river moves at 4 meters per second downstream. His actual velocity, what someone watching from the bank sees, is the vector sum of both. Think of it like this. You're walking on a moving walkway at an airport. Your legs move you forward. The walkway moves you sideways. Where you end up depends on both. This is exactly what happens to Arjun. Two velocities, one actual path. This is relative velocity. Let's take two different cases. Two boats are trying to cross the same river. The river current flows toward the right with a speed of 4 meters per second, and each boat can move through still water with a speed of 3 meters per second. Case 1. Minimum time. In the first case, the boat is pointed exactly perpendicular to the riverbank. So the entire 3 meters per second speed is used to cross the river as quickly as possible. But the river is still flowing sideways at 4 meters per second. Because of this sideways current, the boat drifts downstream while crossing. The actual motion becomes diagonal, combining 3 meters per second upward and 4 meters per second sideways. Using vector addition, velocity square resultant is equal sum of velocity square of boat and velocity square of river. The resultant speed becomes 5 meters per second. So the boat reaches the other bank quickly, but not directly opposite the starting point. Case 2. Shortest path now. In the second case, the boat is aimed slightly upstream at an angle theta. This time, part of the boat's 3 meters per second speed is used to fight the river current. The upstream horizontal component balances the river flow. So the sideways drift becomes 0. As a result, the boat moves straight across the river and lands exactly opposite its starting point. This gives the shortest possible path across the river, even though it takes slightly more time than case 1. Same river, same boat speed, but different vector directions create completely different results. Another case. A small wooden boat attempts to cross a wide river. The boat can move at 5 meters per second relative to the water, but the river current itself is flowing downstream at 10 meters per second. To reduce drifting, the boat is aimed 30 degrees upstream. The blue arrow represents the boat's own velocity. The massive orange arrow shows the much stronger river current. Now let's break the motion into components. The across river component of the boat's velocity is v across equals 5 cosine 30 degrees, which gives approximately 4.33 meters per second. This component is responsible for carrying the boat toward the opposite bank. The upstream component is v up equals 5 sine 30 degrees, which equals 2.5 meters per second. But the river current is flowing at 10 meters per second. That means the upstream correction is too small to cancel the river flow. So a perfectly straight crossing becomes impossible. Instead, the boat follows this curved yellow trajectory, the path of minimum possible drift. The white dashed vertical line shows the ideal straight across path that would happen if there were no river current. But in reality, The river continuously pushes the boat downstream while it crosses. The time required to cross the river is T equals river width divided by across river velocity. So, T equals W divided by 4.33 seconds. During this time, the river keeps dragging the boat downstream. The minimum downstream drift becomes d_min equals river drift velocity multiplied by crossing time. Substituting the values gives d_min equals 1.73 times the river width. So the boat does reach the opposite bank, but not directly opposite the starting point. It lands far downstream because the river current dominates the motion. This is the power of relative velocity, where motion is determined not by one velocity alone, but by the vector combination of every motion. So, in conclusion, the riverboat problem can lead to 3 completely different outcomes depending on how the boat is directed relative to the river current. In the first situation, the boat is aimed straight across the river. Here, the entire speed of the boat is used to cross the river as quickly as possible. That is why this case gives the minimum time of crossing. But because no part of the boat's velocity opposes the river current, the boat drifts downstream while crossing. So, fastest crossing, but maximum drift. In the second situation, the boat is aimed slightly upstream. Now a component of the boat's velocity acts against the river current. This reduces the downstream drift. And when the upstream component exactly balances the river flow, the boat reaches the point directly opposite to the starting point. This condition gives the shortest possible path across the river. So this case focuses on minimum or zero drift. In the third situation, the river current becomes very strong. The boat now has to aim even more upstream just to keep moving toward the opposite bank. This becomes the limiting condition for crossing. At this stage, the boat can barely make it across. And if the river current increases any further, crossing becomes impossible because the current completely dominates the motion. And that is the key idea behind all 3 cases. The actual motion of the boat is never decided by one velocity alone, but by the vector combination of the boat's velocity and the river current. A simple river crossing becomes a powerful demonstration of relative velocity and vector physics. Let's solve in question IIT JEE 1988. A boat. Speed 5 kilometers per hour in still water. River width 1 kilometer. It crosses along the shortest possible path in just 15 minutes. One question. What is the speed of the river current? Take a moment. Think about it. What does shortest path actually mean here? Shortest path means the boat lands directly opposite. No drift, straight across. For that to happen, the boat must aim upstream, and the river must push it exactly back. These 2 forces cancel. The resultant is perpendicular. Now look at the triangle. The boat's speed, 5 kilometers per hour, is the hypotenuse, not a side. The hypotenuse. The resultant crossing speed, distance divided by time, 1 divided by 1/4, gives us 4 kilometers per hour. Now Pythagoras gives us 5 squared equals 4 squared plus VR squared. 25 minus 16 equals 9. And the square root of 9 is 3. The river flows at 3 kilometers per hour. A perfect 3-4-5 triangle. The most elegant answer in JEE history. And the key, knowing which triangle the problem belongs to. Shortest path flips the hypotenuse. Get that right, and the problem solves itself.